A binary star system. One is a void dwarf, another could be a main second star or jet giant. But the little one, the void dwarf, is more powerful. It has a great attraction power so that it can attract the gas, the mass from the companion star, consume it over time, and the two star merge. Okay, the two star merge, and when merging, the speed of the particles inside the star accelerate to very high speed, uh, activating the runaway nuclear fusion. The fusion is so strong that can make the star explode. Okay, accrete the mass from its companion star. Yeah, yeah, that basically enough.
Oh, okay.
And the point, just try to memorize the main idea, huh? Yeah. If you can add some more detail, like the companion star could be a Mexican star or a giant.
Mm.
A giant. Okay. I've seen the mark scheme somewhere. This is kind of recent past paper, like 3 years ago, probably in 2019. Okay, let me check that. 2019 past paper 3. My paper 3 times on 2. I need to open the mark scheme. Okay, this question 2219 Hubble constant. Okay, it's not in 2019. Okay, here, standard candle. Explain the formation of type 1A supernova, which enable the star to be used as a standard candle. The mark scheme here. The reason that the type 1A supernova are used as standard candle is because the interesting thing, just so strange, we don't know the reason why. The peak, the highest intensity, the highest luminosity of these type 1A supernova are almost the same, no matter their size. It's like when when merging, when the mass of that star reaches a limit, which is called the Chart-Krasenka limit, the star explodes, and therefore Chart-Krasenka limit. Okay, here, about 1.4 times the mass of the sun. Okay. In astrophysics, maximum mass theoretically possible for stable void dwarf star, for a stable, meaning below this limit, which is 1.4 times the mass of our sun, the void dwarf exists and stable. But over that mass, the void dwarf can explode. Okay.
Okay.
According to this website, void dwarf star, what's the meaning of that? Comparing to Wikipedia. What happened to a star when the mass over that the star explode? Again, the peak luminosity of these supernova are the same, almost the same. When they explode, the mass just over that limit, 1.4 times the mass of the sun.
Okay.
Okay. A standard candle, what does it mean?
That you use that you use a star as a comparison for other stars that you observe in the observable universe.
Supernova, yeah. But it have one a supernova. Standard candle, astrophysics. Okay, we can measure the peak luminosity of that star, and actually we can measure the apparent brightness at the position of our Earth using a telescope, meaning we can measure directly the value B here. Okay, the brightness, apparent brightness. Its unit is watt per meter square. It means the amount of energy that the device, the telescope, receives in 1 second per meter square area of the collector. Okay, we can measure that directly, the apparent brightness, and we already observe a lot of type 1A supernova during the past 30-40 years, And we already determined the maximum value of those supernova, which are almost the same, which is the value L. Okay. So knowing L here and B, we can determine D from this formula, which is the distance from our Earth to that supernova. Okay. So that is the idea of measuring the distance in the universe using type 1a supernova as standard candles. And the value of the peak luminosity of those stars, I don't know if it is given in booklet or check it. I don't think it is given. Okay, here. This is the ratio, compare the luminosity of type 1a supernova with the luminosity of our sun, which means the peak luminosity of the type 1a here, the blue curve, is about 10 to the power of 9.6, 9.7, compared to the luminosity of our sun, okay, which is that single supernova equivalent to a billion sun.
That's a lot.
More than a billion sun. The energy it emits is equivalent to a billion suns. Okay. Unimaginable, huh?
Yep.
So the peak luminosity is given on this graph, and the formula D, similar to the video, huh? We have in the video, the L is 4 pi d square multiplied with B. Yeah, we need to square both sides. D square, D will become D square. And this formula, I think, is given in the booklet. Here. From the apparent brightness B, which we measure directly, and the peak luminosity we known, okay, a billion times the luminosity of the sun. And the luminosity of the sun, do we know it? Like from the first pages. We have a thing called the solar constant. Looking for that thing here. This one. The solar constant S is the apparent brightness of the sun observed on Earth on average. Multiplying this thing, it means this is the B apparent brightness of the sun. Okay. From this thing, we can calculate the luminosity of the sun, which is this is apparent brightness B, S here equivalent to B, equal to B, and B. We have the formula L equal 4 pi d square multiplied with that B apparent brightness. In the formula booklet, it is a small b. Okay, small b. So we have this thing. We know the distance from the Earth to the Sun is 1.5 times 10 to the power of 15, already given below in here. Unit conversion, the astronomical unit, 1,500,000,000 kilometers from the Earth to the Sun. Okay. Nó có một bài hát gì khá là hay, một bài hát của Jason Mars về mặt trời. Thầy tìm sao ha? Tôi tưởng rất là thích bài hát đó. Jason Mars something. Sun. Okay. 93 million miles. This is the distance to the sun. Okay. Equivalent with the number 1.5 times 10 to the power 11 here. So plugging that value into this formula, square it, multiply with 4 pi, and multiply with the solar constant 1.36 times 10 to 3 here, we get the luminosity of the sun. Okay. And then multiply with this luminosity with 10 to the power of like 9.7, we get the peak luminosity of a type 1a supernova. Okay. Return to the question. Show that the distance. Okay, I was talking about the paper in 2019 here. Explain why a type 1a supernova is used as standard candle. Okay. The answer is the peak luminosity of those stars, type 1a supernova. Wait, no, not this one. Question 20, huh? 21. 21A. The peak luminosity of those type 1A supernova is the same. Okay. Because if they're different, there's no way that we can know what exactly the value of the luminosity there, and we cannot measure the distance. And I've just explained here on the data booklet about how to calculate the peak luminosity of the type 1A supernova, multiplying the luminosity of the sun with 10 to the power of about 9.7. Okay. And return to this question. Question B1 show that distance to the supernova approximately 3.1 times 1018 meter. I do it once, and then I erase it and let you do again, or I will give the instruction, the steps summary. We have here the peak luminosity of a supernova, which is 5 times 10 to the 5 of the luminosity of the sun, also given. Meaning we know the luminosity of that type 1A supernova by multiplying this thing with this value with this value. Okay. And this luminosity is equal to 4 pi d squared. D is the distance that we need to find. Okay. And multiply with the parent brightness d here, with the parent brightness here, this value. So basically just plug the value into this formula and we can find the distance d. Okay, let's do that, write the solution here. In the meantime, I will look on the internet to find the mark scheme. Mm-hmm. 4 by and D, use the calculator, huh?
We can use calculators for paper 3, right?
Of course, yes.
Okay.
Okay, 3.1, which is typically, which is, yeah, almost the same. The mark scheme is 3.07. Rounded up to, yeah. How many seconds here? 2. Yeah, exactly. Good. Not difficult, huh?
Yeah, not really.
B2, state one assumption made in your calculation. Okay, the assumption is that the energy is emitted uniformly in all directions, and there is no loss of energy during the propagation, the transfer of energy. There's no absorption of that energy from a supernova by a nebula, a gas cloud in the universe, or consumed by another star or a black hole. Okay, one assumption I think is the energy emitted uniformly, meaning with the same density in all direction, the same density. Okay, and here the mass scheme say type 1A supernova can be used as standard candle. There's no dust absorbing light between the Earth and supernova. Yeah, the thing that I just mentioned. There's no dust, no nebula absorbing the light between the supernova and the Earth, transferring from the supernova to the Earth. That is more accurately compared to the assumption here about a uniform emission. There's no absorption by a nebula, a dust gas cloud in the universe between the supernova and the Earth.